there's some guidance put in place from Icao and other organizations to reduce these emissions, and I guess you will talk a little bit about that. Different measures, we can improve the operation of the aviation industry, reducing a little bit the CO2 output, work on technologies. I think we heard about from some panelists about what can new technologies bring to reduce CO2 emissions. And then we have sustainable alternative fuels and some market-based measures. So today we are in 2020, and 2020 is the time where we wanted to start to have carbon neutral growth. So even if the aviation industry grows, we don't want to continue to put in more CO2 emissions. So basically our target is this line here. And then there are additional objectives, for example, to reduce the emissions by 50% by 2050, which is then even more difficult to achieve. So it's a good point in time to talk about green aviation, and I think this is why we are here today, and this is why I put the speech to you, and I give you this if you want to.
If I stand. Good afternoon, everyone. So my name is Neil Dickson. I'm Chief Environmental Standards at Icao, and thank you for the introduction. It's a perfect segue into this presentation. So I could talk a lot about Icao's work and the international work going on in terms of standard making, because it covers noise, local air quality, and CO2 emissions, and I'll go into some detail of all of that, but I'll really focus on climate. So for those of you that might not be familiar with Icao, we're an organization of 193 member states. So a global organization. Those member states are effectively our bosses. Of course, we work very closely with industry partners and aviation stakeholders, but we're a UN specialized agency made up of 193 member states. And our vision is to achieve the sustainable growth of the global aviation system, and we serve as a global forum for all states and international civil aviation stakeholders to come together to discuss the way forward on international aviation. Now, to do that, we cover 5 strategic objectives: safety, security and facilitation, environmental protection, which is why we're here today, air navigation capacity and efficiency, and the economic development of air transport. A wide set of objectives. I think you'd agree. I should just point out also the history of Icao. Icao is an agency that's formed by virtue of the fact of the Chicago Convention being signed in 1944, and has been based in Montreal for its entire history. So it's headquartered here in Montreal with regional offices spread out across the globe. Now, what does that really mean in terms of environmental protection? Well, we have a whole cascade of policy documents in Icao that are agreed by our member states. They start with, of course, the Chicago Convention that gives us our reason to exist and the core part of our operation, and then assembly resolutions across all those 5 topics that I've talked about. On environmental protection, we have 3. One general one for local air quality and the general provisions on environment, one on climate change, and then one specifically on our carbon offsetting scheme for reduction in international aviation. Now, when we get beyond those assembly resolutions, we also have standards of recommended practices. That's what we really do best in Icao. I should recognize 2 of my colleagues from Icao here. Maybe they can help me out with a number of SARPs that we have, but I think it's something like 12,000 standards and recommended practices in Icao across all the strategic objectives. Well, in environment, we have Annex 16. That's the basis of our standard regime on noise, aircraft engine emissions that impact local air quality, an aeroplane CO2 emission standard, and then our carbon offsetting scheme. And then we have a whole myriad of guidance material to help the implementation of that across all of those topics. But what are our actual objectives? Well, they're to minimize the adverse effect of global civil aviation on the environment. And within that, we have 3 subsets: to reduce the number of people impacted by aircraft noise, to limit or reduce aviation emissions that impact local air quality, and to reduce the impact of aviation on the global climate. And actually, we also contribute, our work contributes to 14 out of 17 sustainable development goals. So I said I'd focus on climate. I could spend a long time talking about noise and local air quality, but in order to address the climate impact of aviation, in our assembly in 2010, we defined what we call a basket of measures. A basket of measures that includes aircraft technology, operational improvements, sustainable aviation fuels, and at that point, a global market-based measure. And I'll go into a little detail on each of these. But I think it's important to say that on aircraft technology in 2016, we set the first global CO2 certification standards for new types and in production types. Obviously, this reflects the fast-paced development of technology in the industry and tries to account for engine development, airframe developments, and aerodynamic developments. We also have provisions on operations. And in our air navigation part of Icao, we work on a global air navigation plan and an aviation system block upgrade. And then specifically in environment, we also have had events on green airports. And we also have developed procedures on air traffic management, and I'll go into a little bit on that too. Sustainable aviation fuels. You already showed the chart to show the overall picture of the sector. This is the biggest wedge in the chart. So far, we've had about 200,000 commercial flights on sustainable aviation fuels. These fuels are drop-in. They are used with the current fleet of aircraft. We have 6 conversion processes to get there, and currently there are 7 airports distributing these drop-in fuels. And then finally, our carbon offsetting and reduction scheme, or CORSIA. So we've seen this chart. We've just seen this chart from Anna, and you'll see the growth of the industry is, of course, rapid. Our aspirational goal is carbon neutral growth from 2020, and all these measures, whether it's technology, operations, fuels, or CORSIA as a global offsetting measure, will bring us down to that 2020 carbon neutral growth. So from a technology perspective, what do we really mean? Well, we've seen leaps and bounds from the industry, and no doubt that will continue, whether it's high bypass ratio engines or maybe more recent open rotor technology that we might see in the future. We see aerodynamic improvements across all the aircraft that we fly on daily. This includes very obvious changes like winglets, but we also know in the future that we might see laminar flow technologies and so on. And of course, structural design and materials. So we've seen a rapid increase in composite material use, carbon fiber use by the industry, and that's shown on the aircraft that we fly in today. In terms of operations, Icao has a number of policies that reflect a number of ways of reducing fuel burn when it comes to operations. I mentioned our aviation system block upgrades. This represents just a subset of some of those aviation system block upgrades. We also have our global air navigation plan that covers climb, cruise, and approach phases of flight to really show what the industry will do next in terms of changes to the aviation system. Sustainable aviation fuels. So by far our biggest wedge on the chart. Now I mentioned the word drop-in fuels. So these are used in conventional aircraft. They ensure the compatibility and ensure safety and certification standards are met. But of course, there are a number of different challenges that include the maturity of the technology, the research and development, and of course, the feedstocks used from a sustainability perspective. And currently, Icao is working across particularly the sustainability part. But we also have policies on leveling the playing field in terms of cost when it comes to sustainable aviation fuel. So by drop-in, we mean that it's usable in the current conventional aircraft. So no technical changes to the aircraft. Basically, chemically identical to kerosene. Yeah. So a different feedstock, a grown feedstock, or a waste, or a forest residue, or some kind of biomass to produce the fuel. And as you can imagine, this can generate some reasonable advances in terms of CO2 reduction. Actually, sometimes even in ahead of the actual CO2 produced at the tailpipe of the aircraft, because of course, when you burn the chemically identical fuel, you produce an identical amount of CO2, but the saving comes from the life cycle savings when you actually produce the fuel. So now CORSIA, the carbon offsetting reduction scheme for international aviation. This is what's really been occupying our time for the last few years, representing an entire Assembly resolution agreed in 2016, and then standards of recommended practices to underpin CORSIA agreed over the last few years. This is a complementary measure. The other three measures really are in-sector reductions. So what the industry can actually do to reduce, and this will give us a way of offsetting while all those measures come to the fore. Sustainable aviation fuels is key here because the R in CORSIA means reduction, and the reduction here will come from sustainable aviation fuels. So as the industry grows above carbon neutral growth in 2020, that growth will represent the offsetting obligation for the industry. There's lots of details inside of that, and I could spend hours talking about this in terms of CORSIA and its voluntary phases and then its mandatory phases leading up to 2035. But broadly, that wedge as it increases will represent the offsetting obligation, unless you use sustainable aviation fuels. And then your offsetting obligation will reduce. So CORSIA in that way will encourage sustainable aviation fuels into the marketplace. And where we stand now in 2020, of course, highlighted at the beginning, is the beginning of this carbon neutral growth, and it's the beginning of CORSIA. So in this year, the baseline will be set, and then the growth will be calculated going forward to 2035 and offset in an international marketplace. So what I wanted to talk a bit about is what we're doing next. So we have agreements across all the main pillars of environment in Icao in terms of noise, local air quality, and CO2. What we were told at our last assembly by our member states was to prioritize a long-term goal for aviation. Now, we're still waiting on the details behind that, but a reasonable way forward is an interim step while we're waiting for that agreement is to do a stock taking of where we are in terms of CO2 reductions from technology, fuels, and operations. So the in-sector reductions that we can achieve. So not CORSIA, but across the measures that the industry can actually enact itself. And so on the 28th and 29th of April here in Montreal, and of course I invite you all to come and participate, we'll have multiple parallel sessions across 2 days to really hear what the Icao member states, industry, airlines, civil society, investors, researchers, innovators, so on, all people are welcome, are going to do in each one of these spheres. So it's a real stock-taking exercise for the industry. And in terms of a little bit of the content, there's a lot more detail on our website. Of course, we set the scene in terms of leadership of the industry. That's a typical thing that we do in Icao, and it really paints the picture, I suppose, a little bit like I'm trying to do now. But we're focused on technology, so advanced aircraft, so maybe the more evolutionary concepts on tube and wing designs. Then we'll go into novel concepts. We hope to hear about blended wing bodies, hydrogen-powered aircraft, what we might see in the future. We'll have sessions on operations, so air traffic optimization, so more optimization of the system, and then more efficient piloting, so flight efficiency improvements. We'll also have a whole range of sessions on sustainable aviation fuels. So we actually ran a stock-taking seminar a year ago here in Montreal, only on sustainable aviation fuels. And the great and the good of that industry came to us and told us where the industry might go out to 2030 and 2040 and how much fuel they may well have. We also would quite like to hear about boosting this innovation and implementation. So not just the people that develop the technology, but also the people that maybe collate information on the technology and describe the stories of the technology moving forward. And then, of course, the all-important financing emissions reductions. But that just leaves one out that I just wanted to mention. One very important part of this, when we talk about novel technology, and I'm sure in this session we'll hear about electrification of the aircraft system and maybe hybrid and electric power. We would also like to hear in this session about that, but also about the clean energy infrastructure, how you actually achieve your CO2 reduction goals with clean energy, how you get the energy to the aircraft of whatever scale we might be talking about. And we can talk about the technical limitations of lithium-ion batteries and so on, but getting the clean energy to the airport to deliver it to the aircraft will be key in the future, no doubt. So that's it for me. All our latest and greatest work is captured in this document. I hope you like the artwork on the front. It's an Italian graffiti artist called Milo. We like to be a bit progressive sometimes in Icao for an organization that is maybe a bit formal. Look at the people only wearing ties here at the moment. All our work is captured here and it's available on our website, and we're happy to answer any questions you have about it. Thanks for your attention.
Thank you. Do we have already some questions for our first presenter? Okay, so then we go ahead with our next presentation. So I think that was very interesting to set the background. So now we're going to talk a little bit about advanced aerodynamics and with Dr. Vermeire. Thank you. You can take the...
Right, so to follow up on the last speaker, I guess the work that my group does fits in sort of the advanced technology sector there. So basically, how can we design more efficient aircraft as a whole, right? Not focusing specifically on the fuels, but on the aerodynamics of the aircraft, the performance of the engines, maybe different types of engines, that kind of thing. So what we're motivated by in my group is, as some of the previous talks touched on, is that if you look now, air transportation moves somewhere around 4 billion passengers every year. And this is growing rapidly, I think at around 5 or 6% annual growth rate. So that's quite extreme. And the challenge with this is in doing so, it produces, I think, somewhere around 800 million tons of CO2 this year. And going forward, unless the changes that were mentioned before are enacted, it's expected that this number will keep going up. And it was mentioned that currently aviation contributes somewhere around 2% of CO2 emissions, but that also corresponds to somewhere around 4 to 5% of radiative forcing. So it does have a significant impact on the environment. And if we look with current technology, if you make some kind of projection of the increase in the number of passengers per year, if we stick with current technology, we would expect that the emissions from aviation would quadruple by 2050. So this is a huge increase. You go from single-digit percentages up to probably double-digit percentages in terms of contribution to greenhouse gases. So what we're looking at in our group is how can we design improved aircraft, so improved in terms of performance, more efficient, lower fuel burn, those kinds of things, at reduced cost and risk. So here, cost and risk, what I'm referring to is in the engineering design cycle. And I think a couple of companies in Canada and the US in the last year have really learned that there's significant costs and risks to designing a completely new aircraft. So in trying to design new aircraft to reduce emissions, you really put yourself in a vulnerable position sometimes. So we're not the only ones working on this kind of thing. There's a number of different frameworks from NASA, the EU, and Canada, and really there are multi-billion-dollar projects globally to try to reduce the environmental impacts of aviation. So for example, NASA had the Environmentally Responsible Aviation Program, or the EU has the Clean Sky Joint Undertaking, which was just renewed, and then in Canada we had the Green Aviation Research and Development Network. And what a lot of these have focused on in terms of the technological advancements is transitions away from kind of conventional aircraft designs. So for example, if you look at the 787 or the A380, maybe the two most modern aircraft that are flying today, they look very similar to something that would have flown in the 60s, right? You've got typical wing and tube type design, you know, different types of engines, that kind of thing. And what we're focusing on is how can we make sort of a transformative or step change in the types of aircraft technologies. So things like blended wing body configurations where you don't have kind of the conventional tube and wing sort of system, which is now becoming possible with composite materials. You've got things like distributed propulsion or electric propulsion, so moving away from, you know, a pair of underwing engines to this kind of distributed propulsion system. Or boundary layer ingestion, all of these kinds of different technologies that are coming down the pipeline that are much different from conventional aircraft designs. So from an engineering perspective, this is challenging. It means we need improved design of very complex systems like landing gear, high lift configurations, flow control devices, really understanding blended wing body designs. So really kind of a big change in terms of design. And the same thing for propulsion technologies, right? So moving away from things like, you know, ducted turbofans up to, let's say, electric propulsion, distributed propulsion. These are all new designs. And the challenge from an engineering perspective is they're associated with complex physics. So you've got things like compressible flow, shock waves, turbulent combustion, all kinds of different complex physics. The other thing that's challenging that we look at in my group is how can we use modern high-performance computing to do this efficiently? So things like, you know, massively parallel computing systems, things like GPUs and systems composed of clusters of CPUs, as well as how can we leverage things like big data and machine learning to try to make our models more accurate. So what we're really trying to come up with is a new generation of simulation tools that tackle these complex physics. So things like unsteady turbulent flows, complex geometries, physics like combustion, turbulence, and shocks. And we need this to be applicable on modern hardware architectures so we can scale to sort of thousands of compute cores. And we're doing this kind of in three phases. The first of these I define sort of the innovation phase. So this is really the pen and paper type of work that we do in my lab, but also transitioning up to kind of demonstration, let's say realistic applications by using large computing systems, and then ultimately up to industrial adoption, so trying to get industry to use these tools. So in doing this, we contribute to the development of two different computational aerodynamics codes. One of these is HORUS, which stands for the High Order Unstructured Solver. And then we also co-developed PyFR, which is an open source computational aerodynamics code developed in collaboration with Imperial College London, Texas A&M, and Tohoku University. So here's a few just kind of examples. I thought it'd be best to show by example the kind of things that we do. So here's an example of a complete aircraft configuration where we've done the aerodynamic analysis of the flow over this aircraft. Something like this takes around 15 to 20 minutes. And now what we're looking at is going towards unsteady simulations. So here's another example of flow over a row of jet engine turbine cascades. So these are the last few rows of turbine blades in a jet engine. We're able to do unsteady simulations, capture complex physics, things like turbulent transition, the propagation of the wake behind these blades, and then ultimately how these blades interact with each other. So really trying to understand the physics better that will help us that will enable us to design more accurate aircraft components. We've also been looking at aeroacoustics. So here's an example of the exhaust from a serrated nozzle on a jet engine. And here we're looking at the flow field behind that nozzle, right? And of course, as this jet comes out of the nozzle, it also produces acoustic waves. So here's the sound waves coming out of that engine. Here again, you've got the serrated nozzle, the jet coming out the back, and all of these waves that you see are sound waves that are propagating away from the engine. So, just like we want to improve the efficiency of these aircraft, we also want to reduce the amount of noise. And we've also been applying these technologies to other types of related fields. So for example, wind energy. Here's an example of a vertical axis wind turbine, a pair of blades that are rotating around and trying to predict the power that's generated by this. Obviously not an aviation application, but very similar in terms of the physics, looking at the performance of these blades. So hopefully that gives a summary of the type of work that I do and what our expertise are. Thanks.
Thank you very much. Do we have questions for Dr. Vermeire at this point?
Sure.
Yeah.
Are you using any type of artificial intelligence to aid in aerodynamic computation?
Yeah, so in those simulations, there's nothing like that being leveraged there. The challenge with the unsteady simulations is that they're very expensive. So what we're trying to do now is use artificial intelligence to learn if there's some background physics, can we get some insights into the physics from those simulations that let us do much quicker and more inexpensive simulations, right? So to try to leverage that huge data set to let us do things more quickly. Yeah, so that's a project that's happening right now, but no cool videos from it yet. Yeah. Yes?
What Aurelis model do you use?
Yeah, so all of those results are DNS or LES.
Oh,
yeah.
So you have a big cluster too.
Yeah, so for example, the turbine blade simulations were run in collaboration with the Department of Energy in the US. So we got access to the largest system that was available there, and we could use the whole thing. But from an industry perspective, that's not really practical. So that's why we're looking at trying to leverage, let's say, machine learning to kind of lower the bar in terms of computational cost. Yeah.
You mentioned the non-CO2 impact of aviation. Seems to me that maybe your tool set could lend itself to maybe the modeling of contrail formation, both the linear type contrails to more persistent contrails behind the aircraft. Because there's an engine dynamic component to this, there's an aerodynamic component to this, and of course a huge atmospheric component. Have you thought about that kind of thing?
Yeah, part of my background is actually in atmospheric sciences, so I did sort of thunderstorm modeling and that kind of thing. And we're actually looking, one of my PhD students, at basically that topic, not specifically on contrails, but one of the challenges with contrails is that they persist for such a long distance behind the aircraft. So from a simulation perspective, it makes it very expensive. So one thing that PhD student is looking at is how can we do kind of adaptive techniques. So let's say, an aircraft passes through a particular region of space. How can we, let's say, adapt or refine just where the contrail is so we can simulate that accurately to reduce computational costs? So he's shown you can get, maybe 3 to 10 times reduction in computational cost with the same level of accuracy. Yeah. Yeah.
So you mentioned that eventually the goal is to sort of mature these methods for industrial adoption. So from the context of, say, conceptual design of an aircraft, these tools, these CFD codes, will they enable, say, during conceptual design to go through a lot of these new type of configurations very fast, or is it both speed and cost?
Yeah, so usually when you're designing an aircraft, let's say you're going from conceptual design to detailed design, right? There's a whole span of types of tools that you use and how accurate they are. So usually a conceptual design, you'll use a tool that's relatively inexpensive, but it'll get you, maybe within 20%, 10 to 20% of the actual aircraft performance. And then when you go out to the detailed design, now you're really talking about, fractions of percent. But if you go back to that, if you can introduce more accurate tools much more early in the design cycle, so let's say bringing these kind of high fidelity tools right up front when you're trying to do the conceptual design, the hope is that it will lead you down a much better path, right? So instead of, let's say, starting with, we're going to use wing tube type configuration, if we have conceptual design tools that let us look at blended wing body and all these kind of different ranges of concepts, it will hopefully lead us down a more accurate path towards kind of a true optimal design. Yeah. Good.
I have another question. Sure. You said these tools will help to better describe the complex physics, and one of the key aspect of this new configuration is, for example, to reduce the drag of the aircraft and to have a better prediction of that. Do you have already made the link? How good are these tools to actually predict the drag, and then that it help to find a good configuration of the aircraft? Is there also work in this perspective planned?
Yeah. So let's say the unsteady part. We haven't looked at a full aircraft configuration with the unsteady solvers yet. But we've looked at some examples for, let's say, just a simple stalled airfoil, where classical techniques will be off by maybe 20 or 30%. When we use these sort of unsteady simulations, we can get within 1 or 2% of the actual value, let's say, for drag. Which means that ultimately what you design on your supercomputing cluster, when you go and test it and fly it, you're much more close to reality, right? And so in that, if there's a big gap between those two, then if you do a lot of optimization on the computer, it doesn't really mean anything. Yeah.
Yeah. So in the end, it would give you, this is really this reduction in risk as well, because you could go to more unconventional configurations because you have a better prediction.
Right.
Because this is one thing we see, and I will talk a little bit about that, is that there's all this prediction of these new technologies that would help to reduce the CO2 emissions, but no one is actually, people are doing some prototypes, but no one actually wants to take the risk and to go ahead and, because there's so much uncertainty involved. So
yeah, I mean, you're talking for a new aircraft like tens of billions of dollars, and if it's a completely untested technology, it makes it difficult for a company to follow through with that. So the hope is with these, we can get much more accurate results digitally, which is much cheaper before you try to fly the thing and find out how it actually performs. Yeah.
Okay, thank you. Other questions? No? Then we continue. Thank you.
Yes, I'm continuing on what was discussed before. I'm in the same department, mechanical, industrial, and aerospace. My area is mainly in multi-phase flows, and also their application in functional coatings. I can give you a few examples of what we have done in the past, let's say, decades on improving the performance, especially in the emission part. This is a project we had with Pratt & Whitney Canada on their atomizer, so spray atomizer. As you know, for emission, even 1% improve in the engine, it is huge. The impact on the environment, or even 0.5% is huge. So what Pratt & Whitney was interested in is to change this engine. This is about 50-year-old engine. It's one of the most used engine in aerospace industry, just to change their atomization pattern. Atomization is what we use when we have a liquid fuel. We atomize it to small drops, and then the smaller, the better. So evaporation is faster, mixing is better, efficiency of combustion is better. So our role was to improve that aspect. So reducing the time for atomization in terms of the size of the particles was the main goal, changing the conical spray to an elliptical one to reduce the weight, at the same time improve the pattern of atomization. And it was a very successful project a few years back with the collaboration. The CREAC was a big support for that project with Pratt & Whitney. And also Rolls-Royce in India was one of our collaborators in this project. Another topic that was also, my group was contributing to this, was in biofuel, and we started with biodiesel and compared with diesel because it was easier to work with. One of, actually at that time, was really the goal was drop-in, as was discussed by the first presentation. So really the challenges that it's associated with biofuel, and we looked at biodiesel and diesel at the same time. This is a cross-flow condition that we usually have in any engine. So you have liquid coming in, and cross-flow air is atomizing the fuel, and finally you will have droplets. When the droplets are evaporated, you will have combustion, and you generate energy. So here you can see the difference in, actually we did both numerical and experimental. So the left side, for example, I don't know where the pointer is. Oh, this one. Okay, I don't want to tell. So this is the numerical result, and side by side you can see the experiment. We could capture the main physics governing the problem of atomization and breakup, which is key for improvement of any engine performance. And you can see in it's completely different flow regime. We call it in multi-phase. It's a different flow regime, and the challenges associated when you have a bio case compared to a classical or conventional. And was interestingly, we had a big group of researchers at Polytechnique LCA was done for this kind of drop-in fuels, and the result was very, challenging and interesting at the same time. So Again, it's a very, very interesting topic in aerospace-related material for see where the biofuel is coming from, how it is going to be distributed, how it's going to be used, and how you can make up, because imagine you have the same fuel, you really want to atomize it the same way. You cannot afford having different performance for the engine. In terms of functional coatings, we have been using thermal spray. We have one of the probably largest thermal spray lab in academia in the world, and we are very proud of that lab to develop coatings that are performing in terms of thermal barrier coatings, wear resistance, and also preventing surfaces to form ice. So what is thermal spray is basically you have a spray gun that generates high temperature, high velocity gas by plasma, by combustion, and so forth. And what you do, you inject powder to form protective coatings. These protective coatings are key factors in aerospace, specifically if you look at different positions, especially in the engine part. Parts that are coated with these type of coatings to increase the resistance of the part in heat and also corrosion, erosion. By increasing this resistivity, you can increase the temperature of the engine and increase the efficiency by up to 2%, which is huge in terms of performance of the engine and saving and CO2 footprint. Actually, I remember one example was the thermal barrier coating by thermal spray saves few Olympic size pool of fuel per day for the aircraft when it travels. So this is playing a big role in aviation, and we are working with Pratt & Whitney Canada, Pratt & Whitney in the US in developing new thermal barrier coatings that they have much better performance in terms of lower thermal conductivity and durability. This is our thermal spray lab, which has 2 spray booths equipped with almost all the equipment that you need for different types of thermal sprays. And what they can say, another topic that we were very much successful and very much busy with is in-flight icing, which generates increased drag, lower the lift, and of course, not only safety. In terms of the size, especially mid-sized aircraft, their design is very much affected by icing. Much larger size, they are less critical, but small, mid-size, like Bombardier size aircraft, they are very much affected by this kind of phenomena because their engine needs to be bigger. The design needs to be also on the size and the weight of the aircraft is affected because of the icing. So we were successful with a big consortium in collaboration with Europe. The project name was Phobic to Ice. I was the leader of that project from Canada, and we had European partners. It was about $3.5 million project. Pratt & Whitney was the main company in Canada, and also Airbus was the main company in the European community. So we were successful in forming like 6 coating producers. We were there to develop super hydrophobic and ice-phobic coating and understanding the relationship between the 2 phenomena to develop durable coatings for, of course, aircraft, and also improve ice performance in terms of development of ice, and if ice is formed, how to reduce the adhesion of ice on the surface. And we can simply see by definitely active coatings, we can reduce the amount of ice, and sometimes we can have no ice formation. This is the leading edge of an aircraft, leading edge of airfoil in a wind tunnel that we tested. One side is aluminum, the other one is super hydrophobic, and you can see, but minimum amount of energy you can have free of ice surface, which is critical, especially when we are moving toward hybrid electric. When you have really minimum amount of energy and you don't want to really jeopardize the total energy that you have, and of course, safety of the airplane. So I believe this technology for icing and ice phobicity is the critical thing for future, also not only for medium-sized aircraft, for small size with hybrid electric is one of the new trend, and this is one of the project that again, combination of the same project. This is in INTA in Spain that we tested various coatings with this aircraft under practical condition. So I would like to thank our group, of course, my colleague, Christian Moreau, who will have a lot of common projects together, and the group of students.
Thank you very much. Do we have questions for Dr. Dolatabadi?
Yes.
Very interesting work on the icing aspect. What are the drawbacks of such a system, and has it been used yet on an aircraft?
One of the main challenge remains is we don't have any passive ice-phobic coating. I mean, we never found a coating which is by itself a condition that you run it is ice-phobic. And thermodynamically, it's understandable, but we can have coatings that they are resulting in much lower adhesion of ice. That's what we are already patented a technology, which is, we call it slippery coating. So the ice is formed, but is very loose on the surface. Definitely, in terms of durability, still we are facing a lot of challenges to get there. But it's moving on. Many of them, I mean, Airbus is very much looking for it. We are also looking at active coatings that I showed you one example, that if you have heating, you already have heating element, but you don't need to use a lot of it. For typical aircraft, you're required to have about 60, 70 degrees at the leading edge to have fully evaporative wing. We showed we need only 2-3 degrees C at the leading edge. So definitely in terms of saving energy, there is no question about it. And we have true phobic to ice. We could not come up with any ice-phobic coating, but we came up with 2 or 3 types of super hydrophobic that they were very durable. I mean, durable for aerospace application. So I should say the success was in that direction. So we are there. I mean, I should say TRL 4, 5, if you think about it.
Yeah.
As part of your research, have you come across an increased level of icing for aircraft, an increased risk from a changing climate point of view? Because there's some fledgling research that talks about increased. Obviously, icing is a long-standing problem, but increased levels of icing. So then your research could be more poignant, actually. If you turn the argument around and you look at aviation, obviously aviation's need to deal with its environmental impact, but also the need for aviation to become to adapt to a changing climate. Have you seen anything like that in your?
No, I haven't seen, but it's an interesting point. Yes, definitely an interesting point.
Yeah.
So I just have like a 2-part question. So the first thing is, with this coating that you developed, what is the potential for weight reduction in the aircraft that will lead to fuel burn reduction and less CO2? And is it primarily through the wing ice protection system? And the second thing is, Dr. Vermeire talked about the CFD aspect, and in CFD you can simulate a lot of acoustics. Could it be also possible to say, try to predict using CFD the icing characteristics of the wing, and then determine how much of a coating you need, or is there any synergy between those two works?
In terms of CFD, we do CFD in parallel for detail of ice formation and show how super hydrophobic can be ice phobic or not. We have done some work on that, and we keep working on it. Definitely, it can tell you how much energy. In terms of weight, it's very difficult to say, but it's doable. It depends on. I was talking to companies like Bombardier or Pratt or Airbus. It's different depending on the type of aircraft. And you can go even backward because for the ice protection and standards, sometimes, I mean, some of the aircrafts, their engine is up to 40% over designed for just 1.5 minutes because all the time and imagine if you're really operating in Bahamas, you never have, but still you have that engine, which is 40% over designed because that aircraft should be certified. And 99% of the time, they never even use it because it's not you. But you should, and you have to carry that weight all the time. So imagine if it, and also everything should be designed, and the system, the heating system that is incorporated in the wing, and every aircraft has different case. So the weight, it depends on what kind of anti-icing or de-icing system that you have. It's very difficult to say one when the spectrum is huge. It can be very big, it can be not too big. So a simple answer is for very huge aircraft, weight is not a big deal. It's already there, they have the system. But for mid-size, and I think my vision is, I cannot prove it, but I think for futuristic, for hybrid and also electric aircraft, it can save a lot, and it's critical to have some systems that can, with minimal energy, you can make sure that you have no, and icing is happening when you have relatively low altitude, which is again for hybrid electric, or small aircrafts, it's critical. And we live in Canada, we all know what it means. Maybe it's difficult to sell it to other countries in other parts of the world, but for us, I think we know what it is.
Yes. Just to add to what you say, I think it's another element to it is not only the weight that you remove from the systems, but the power that you stop taking from the engine. Right? So the hot air that you draw from the compressor, which you don't use then for propulsion, and then you have to use to de-ice.
Exactly.
So the saving of that will also give fuel reductions.
Exactly, yes.
And as you said, the system is very particular in terms of the impact on the aircraft design, because, for example, if you design, like if you have a system running on bleed, if you descend, normally your engine is idling, and this is where you don't have a lot of this power to remove the ice from the surface. So this is like where it comes from, that you actually oversize your engine compressor and so on. So it's very demanding. And if you go to electric aircraft, because of this high peak power that you need during takeoff and landing, again, it will size your power generation system and so on. So yeah, especially going forward, it's very good to have this kind of option to maybe reduce this kind of peak power, which is really there for a short time.
It happens really during the peak power. That's the problem, is that during takeoff and landing, that's the most of the time.
And another aspect to that is that the amount of protection you need is also more significant if you have slimmer wings or higher, more aerodynamic, sophisticated airplanes. And so this is also the future. So, if you want to really have an optimized aerodynamic aircraft, you need to have a solution for the ice. So I think it's a very good synergy to look into how these things go together in the future.
So we have a future.
Good
to know.
Okay, very interesting. Other questions? Okay, so we go ahead with Dr. Lloyd.
Is this already on? Yes. Okay. Good afternoon. You've all been very quiet. So, just a brief background. I am in the School of Business, but I also have an affiliate role in the Department of Industrial Engineering. And so most of the work that I'll talk about today is more engineering related. Okay, so just to start, I'm going to give you a brief background. I'm relatively new to Concordia, so I'll walk through some past projects just to give you some examples of the work that I've done. We'll start in the upper right-hand corner. So a significant amount of my work as a consultant or government contractor was focused on looking at the environmental and health effects associated with coatings, both in sort of the beginning application of applying the coatings, but also in the maintenance and repair applications as well. So when we have people removing surfaces and then replacing them. I also did some work on the upper left at airfields and airports, mostly focused on installing renewable energy. I'm doing a lot of demonstration validation projects actually in both of these. So looking at new systems that were being proposed, in the coatings area as well as in the renewable energy area, and then working with teams of colleagues who would demonstrate those technologies and validate them. And my work was really on the side sort of analyzing the effectiveness from an environmental, human health, and cost perspective. And then on the bottom, this sort of links to my current research, and this is really sort of my area of expertise is in lifecycle assessment. And so here, we're looking at So if we have this system, what are the life cycle impacts from cradle to grave? And some of the work was focused on alternative fuels. So looking at sort of what is the net CO2 impact is what we were mostly focused on, but then also looking at other environmental aspects as well. And so then this brings me to some current projects, just to give you a little flavor of what I'm doing now. So in the upper left, is it your left? Yes, upper left corner. This is a project that we're working on right now with one of my colleagues in industrial engineering. And what we've done is we've basically modeled Montreal Trudeau, and we're looking at different types of electric taxiing systems, both onboard and external, and looking at what the impacts would be from a variety of perspectives. So from a cost perspective, from a taxiing time and delay perspective, and as well from an environmental perspective. And so, you know, this particular airport is sort of in an ideal location for external electric taxiing systems because we do use hydropower, and so we, you know, have both the reduced impact from the aircraft powering itself, as well as the reduced impact from not relying on fossil fuels for the external taxiing. And then we're basically going to, right now, we're looking at a number of systems, and then what we'll do is sort of drop this airport in different locations that have different electricity mixes and look at the impacts in those areas as well. One thing to point out is that in all of these projects, while there's a specific thing that we're looking at, technology or policy, we also look at the life cycle impacts. And so we'll be looking at not just the fuel saved from powering down the aircraft and taxiing it, but also the reduced environmental impacts from the production of that fuel, which you often don't see in studies. And it's obviously not as large as the combustion of the fuel, but it's not insignificant. And then also with, you know, from the electricity mix, looking at what are the life cycle impacts of using that electricity, depending on where you're located. In the bottom, this is a project that we completed sort of over about a year ago, but are still sort of finalizing and extending. And so in this project, GE had done a study, a life cycle study, looking at the impacts from some components that they had installed or produced via additive manufacturing. And certainly the predominant savings was in fuel consumption from lightweighting. And so, but what we wanted to do is look at sort of the production end of things. And so one of the things that we see is many of these studies really focus on just the fuel savings, but then they don't look at, well, what are the environmental impacts associated with everything else in the life cycle? And so some of my work will then go sort of into those specific areas. And here what we were looking at, and this was sort of triggered by a conversation with people from the U.S. Department of Energy saying, you know, we have all this work going on in additive manufacturing and this idea that we'll have, you know, decentralized manufacturing in all these different locations. But we're also really concerned about the energy that we're using at these production locations. And so what we did is we basically took that component and extended GE's study to look at different production schemes. So looking at what they're doing now is centralized manufacturing. I think at their plant in, Georgia or Alabama. But looking at what if it was relocated to the various maintenance locations that the LEAP engine is serviced, and what would those impacts be? And so that was a study that we're sort of wrapping up now. And then sort of on the upper right hand, this is just sort of a catch-all for everything else that I've got going on. And again, this is, again, all mostly related to life cycle assessment. A couple of projects are related to developing methods to improve our ability to use life cycle assessment. So for example, when we do these studies and we're looking at the, you know, environmental life cycle impacts or the life cycle cost, one of the things that often gets lost is worker health and safety because we don't have methods integrated into the models that we have now for life cycle assessment. So one of my projects is focused on developing methods for assessing worker health and safety across the full life cycle. Another project is sort of related to this idea of science-based targets. So we're starting to see organizations and governments sort of think about, you know, we do these studies and we see how we're performing and how that performance is relative to some baseline or maybe some other alternatives, but is it good enough? And as a consultant, that was the question that I routinely got. We would do an analysis for somebody and then they say, so am I doing a good job? And we'd say, I don't know. You know, you're doing better than this alternative, better than maybe what you were doing before, so better, but is it good enough? And so this idea of science-based targets is that we look at, for example, climate change, look at greenhouse gas emissions, and we say, how do we allocate greenhouse gas emissions to different companies or industries or countries? And so what we're doing is looking at if we allocate them at a company level or at a unit revenue level or something like that, then how do we assign it, and then can we evaluate companies' performance or a life cycle's performance against that science-based target? So that's a project that we have going on as well. And then there are a couple other projects related to coatings that we're working on, looking at life cycle impacts of evolving coatings or emerging coatings. And from an LCA perspective, we do a good job of quantifying things we know, but we don't do a good job of quantifying things we don't know. And so that's the work that we have going on there, is sort of thinking about how do we do prospective LCA when there are so many unknowns, and do it in a meaningful way that actually helps inform decisions, not after we've adopted the technology or implemented the policy, but before we decide which technologies to adopt or which policies to implement. And that about wraps that up. So if you have any questions, I'd be happy to answer them.
Thank you. We have questions? Yeah?
The electric taxing initiative. So I see the quote, it's an electric vehicle which is charged at the airport.
Yes.
Is this considered for departure as well as for coming back, or just either or?
Yeah, so as far as I know, the specific one that's shown here, I think it's the TaxiBot. I think it's the only one that currently is available for taxiing, pushback, taxiing out, and taxiing in. There are a couple of electric pushback trucks that are just for pushing back, and then we have sort of the onboard electric motors in the wheels. What we're looking at is a bunch of different scenarios in our model, sort of assuming, what if you had trucks that just taxi in, or trucks that just taxi out, or just push back, or if you prioritize aircraft based on their size. So we're looking at a bunch of different scenarios. But as far as I know, I think this is the only one on the market that's.
And the outcome of this study is a quantifiable measure of CO2 reductions?
Yeah, so, well, right now what we're quantifying is taxiing time, because they do operate slower than the aircraft when they're powering themselves. We're also looking at cost and environmental impact. So basically just focusing on emissions. Right now we're just looking at on-the-ground emissions. We're not looking at any potential impacts to lightweighting the aircraft and reducing the fuel that it has to carry. That potentially could be a follow-on study, but right now we're just sort of looking at ground emissions, including CO2 and NOx and hydrocarbons and whatnot. Yeah.
So following up on that question, did you consider any collaborative decision making? So, for example, at Trudeau, if you said that the tax time would be slower. So if you consider CDM, then you might be able to plan the taxiing in and out.
Yeah, so we haven't gotten to that point yet. At this point, it's sort of the first study where we said, okay, let's look at these electric taxi systems and sort of see, based on current technology, where we are. And so the next step might be, this one is semi-autonomous. It basically connects to the aircraft and then the pilot controls it. But what if you had completely autonomous? I mean, there's lots of different scenarios we could go down as well. I mean, I think the main thing is to get the simulation working, and then we can start to throw all kinds of what-if scenarios at it. Yeah.
And in terms of turnaround time, from the top of your mind, do you remember if it increases the turnaround time considerably, or is it like a few seconds or minutes?
Yeah, so I don't want to say off the top of my head. I'm certainly happy to share the results with you. I think, if I recall correctly, when we don't have sort of peak traffic, I think that it's a 20% increase. But then when we have peak traffic in our simulation, it really depends on how many trucks you have, because we can end up with lots of congestion and sort of traffic jams on the runway. And so what we've done now in regards to that is sort of looked at how many trucks do you actually need in order to prevent the congestion from happening. But, yep.
Other questions?
I just have a question about, so with electric taxiing, you're basically taking off the aircraft to the main runway using an electric truck or an inbuilt sort of motor or something. But at the end of the day, the electric power is coming from the power supply to the airport.
It depends on which technology. So, if you're using one of the motors on the aircraft, you're probably using the APU on the aircraft. But if you're using a taxi truck, you're just basically charging it from the grid. So you're just using whatever electricity mix that is coming to the airport. Or, you could also, install on-site renewable energy and use that as well. But I mean, I think there's a variety of challenges. The airport would pay for the towing vehicles, but then the airlines would benefit from the fuel savings. There's lots of different challenges associated with these technologies.
Yeah.
Just to add to that, we actually had some experience of something a little bit like this. We ran a pilot study, one in Jamaica, one in Kenya, and the other one in Cameroon, to electrify a number of gates at a couple of international airports. So then when the aircraft parks at the gate, you can switch the APU off.
Okay.
But immediately, so that's a great idea. You build some solar panels on the side of the runway, on the side of the airport, considering all the safety requirements. You electrify the gate, and then you switch off the APU. But who pays for it? Yeah. That's actually immediately the immediate question. And it's a very challenging thing to address, because the technology is there. It's as you might say, low-hanging fruit, I suppose. But then there becomes all these other issues that you really need to
so I mean, the estimates that I've seen is that taxiing is roughly 4% of energy consumption for aircraft. So, and like you said, the technology's there. It's the infrastructure, and also, so if you start using these trucks, some airports would probably have to add infrastructure. I'm not sure that you'd be able to use the same taxiways for all these trucks that are going out to the aircraft and then the aircraft that are returning. And so again, who pays for that? The airport. So there are a lot of challenges, but again, as you mentioned, it's technology that we have, and we're electrifying the grid faster than we're electrifying aircraft.
Okay, thank you. So I think the last presentation is for me. No, I have a mic. I just need that. Okay. Yeah, I'm connected. Okay, so I will continue where we already talked a little bit about that saving fuel in the future would need new configurations of aircraft and so on. And in my lab, we are really concerned with conceptual design of new aircraft, and in particular with the aircraft systems that consume energy on board. So if you go back, so overall the technology challenges that we try to address are really to try to reduce the fuel burn of the aircraft. And they're basically on aircraft design, there are 3 key levers. There's the reduction of drag, where we already heard it before. Normally it's the people in aerodynamics who take care of it. Then we reduce the weight. There are several ways of doing that, different materials, but also designing the aircraft in a better way so that you reduce weight. And we discussed already that it's quite a challenging and difficult task, especially if you need to do that in conceptual design where you don't have a lot of information. But the better you are in predicting the weight, the more optimized you can design your aircraft and so on. And the third point is the onboard power optimization. So we not only need power to propel the aircraft, so for thrust, but also we need power inside the aircraft, for example, to protect against ice, to provide air conditioning that the passengers survive, to move the control surfaces and so on. For all that, we need the power which is used in the aircraft. So this is the focus of my research group. We're looking into the onboard power optimization of conceptual aircraft in the context of new configurations. So unconventional aircraft configurations, we have seen a lot of discussion about hybrid electric and distributed propulsion, and all that leads to that we actually need more electrical aircraft systems, which is very complex. But all these 3 things, they go together. So in my research group, we are focusing on the aircraft systems, which involve many different systems and the interaction with energy, but in the context of aircraft design and multidisciplinary optimization. And we want to develop design tools that help, especially for this new configuration. So to predict better the weight, to reduce the energy consumption and so on. So there's 3 axes we are looking. One is more about the process on how you design these complex systems, which is complicated, so you need to improve the whole structured process. I will not talk about that today. And we also work on developing new models and tools, for example, for the conceptual designing, so to better predict the weight of these new aircraft configurations, also to look in some thermal aspects, and there will be one video about that, I think, in the FOSS space as well. One of my researchers did a video recording on that, so I will also not talk about that today. But we also look at the integration of some new technologies, and I will talk a little bit about a photovoltaic system. We talked about installing solar panels on the airport, but there might be something if you want to install them on the aircraft, so I will talk a little bit about that. And then Andrew will continue to talk about the hybrid electric architecture and how it impacts. So one of these challenges we have is that it's really very complex. You need to take into consideration many different aspects. And if you want to do this kind of trade studies, for example, as we discussed, so if you put on an ice-phobic coating, how much do you reduce the power consumption? And then how much impact has that on the electrical power generation, and then the size of the engine, and then in the end, the size of the aircraft? You need a lot of, a lot of things playing together, and we try to develop this kind of tools on a high level to be able to do that. Yeah, so today I will talk a little bit about the photovoltaic system in this context. So just stepping back some years, in 2010, there was this project, the Solar Impulse, which demonstrated 26 hours, basically non-stop flying capacity. And so they built an aircraft which has the size of an Airbus A340, basically. The wingspan could house 2 passengers, and it's completely solar panel powered. Okay, so no fuel is burned. And 5 years later, they built a new version of that, and they actually flew around the world. And so at this point in time, I was working at Bombardier in conceptual design, and we were always looking for new technologies and what could we bring into our aircraft. So we started to think about, okay, can we have solar panels on our future aircraft, especially if we want to go to more electric, hybrid electric? Maybe we can, if it's not enough to power the aircraft, but still use this energy which is available if you fly across the above the clouds, to use that and to supply our onboard systems. So actually also this aircraft uses solar cells with an efficiency of around 20%. But we see already in research, it's a very active area of research, that already much higher efficiencies are available in more research type of solar cells. So this is actually like quite a conservative kind of approach, I would say. And so started to look into many different applications of that. So this is a little bit of just some pictures of the work I did with some students on looking at different type of aircraft configuration. First of all, which are the different surfaces where you could install solar panels on? How big is this area? And so then how much power would you get out of that? But then we said, okay, wait a minute, there's a lot of complex surface, there's shading involved, so you don't necessarily get the full amount of power on this different surface. So we looked at different analysis on shading, looked at different aircraft configurations, which of these aircraft configurations are actually good, which surfaces are the best if you want to mount some solar panels on an aircraft, and so on. And then we did some analysis, very high level, to see how much power do you get out of these solar panels compared to the power that is actually installed in electrical generators. So this is what this chart shows here. We can see that on one axis we have the generators that are currently installed in the aircraft, the electrical power they produce, and here you see the amount of solar power you could produce compared to that. And so we see that for small aircraft, like a Cessna, for example, we could get the whole amount of energy that you have in your generator actually by mounting solar panels just on their wing. Okay? And if you look at some smaller regional aircraft, you can see that you get between 80 to 50% out of the power installed. If you look for bigger commercial airplanes, normally they use more electrical power, and so the ratio between that gets lower. Okay? They are also less interesting because they fly normally long transatlantic flights, so we have a night flight and so on. But especially for this area of regional aircraft that normally travel during the day, and so on, it seemed very interesting to look into that. So we continued to look further. So we did some work with sorry, that was not supposed to be like that. Sorry, let me go back. Okay, we did some studies, for example, on the Q400. Here you see like just a picture how the surface would be. And we saw that, for example, for this example, the Q400, which is a Canadian regional airplane, that you can get almost like on average, for a sunny day, you can get 100% of the installed power of one generator just from the solar panels. And normally you have 2 generators just for safety. So actually you could produce quite a lot of power, so around 12 kilowatts, which is the amount you would need, for example, for your air conditioning system and so on. So it's not too bad, I would say. Okay, of course, if you have an overcast day, this power amount decreases. But there are some systems, for example, the air conditioning, that need way more power when the sun shines. Okay, so this led to our next investigation to look at, okay, if we want to use this power intelligently, maybe there are some ways of integrating that into the aircraft and it actually makes sense. So what we saw from the studies is that the power yield we can get is promising, and there is some potential for fuel burn reduction. Okay? We need to consider that these solar panels have weight and so on. That needs to be considered, but it's small compared to other systems like an APU or a fuel cell or other things that I looked into. So we looked at a particular case, for example, for ground operation. We have this scenario that if the aircraft is not serviced, as we see here, on hot conditions on ground, the aircraft gets heat up a lot. And then you actually use either a ground supply from the airport or the APU, which is a big gas turbine installed in the aircraft, to what we do a pull down, so to actually reduce the heat in the aircraft before the passengers can start and come into the aircraft. And so we're thinking, so this creates emissions on the airport, noise, and so on, and it leads to this thermal cycles that you have. So we're thinking if you have solar panels on your aircraft, and you could have like an autonomous air conditioning system that runs all the time without the aircraft being connected, just a fan to keep the temperature at quite a good level. Could you reduce, for example, the size of your APU, or you could get rid of needing the ground equipment, and so you could reduce the emissions on the airport. So we did some more detailed study on that by developing a thermal model of what is happening in the aircraft on ground, and then to go through this whole cycle of if we have solar panels, we reduce this kind of heating up in the cabin, and then we are able to reduce the air conditioning power load and the APU and the air conditioning system sizing and so on. So we did some study on that. There still needs to be some work to be done to do that on many different aircraft, because it depends on the size of the aircraft, but it looks very promising. So the potential would be to reduce airport emissions, to improve the autonomy of the aircraft, but also to improve the reliability, because all these components installed in the aircraft, the electrical power equipment and so on, they would go to less thermal cycles. So it can get up to 70 degrees, for example, in the equipment bay of the aircraft. So if you have this kind of autonomously running fan that stays maybe at 40 degrees, there would be a good gain on that as well. So there are many aspects, many detailed aspects that need to be considered further, but we started to do this kind of concept study in this area. So there's a potential, but there are many things that need to be considered. So I just listed some of them. So that's really like we're at the starting point. So we need to look more into this integration within the whole architecture. And there's many different technologies in terms of the solar cells. Normally, if they are thinner and flexible, they have more efficiency and less weight, but there are others and so on. So it would be depending on where you actually, how do they integrate them in the aircraft structure, which leads us to another topic, more mechanical, on how do you install them? If they break, how do you maintain them? Do you need to remove the whole wing? Or, so there's lots of challenges that need to be understood. Also, how that thermal environment impacts the efficiency and so on. So there's lots of things, but it's I feel it's an interesting topic. But if you look at, for example, all these technology roadmaps, it's not very often mentioned because people say, okay, there's not a lot of efficiency. Maybe it's better if you install the solar panels on the airport, which is also a good idea, but you just mentioned that there are challenges associated. So this is a little bit of work I try to push forward. Unfortunately, it's because it's a little bit unconventional, and we get in all this discussion who wants to fund this kind of forward-looking research. Is the gain really more than if you look into other technologies? So something to look at. So going back, so this is one of the topics we look at, but by developing this kind of tools that help to investigate these technologies for many different configurations, we want to basically give the aircraft manufacturers the opportunity to look at that for their next concept and to see how that might bring a benefit. So now I give Andrew will continue with some words about the hybrid electric, which is a very good combination to that.
Okay, so just basing off what Susan said, I'm going to show some of the other work that we're doing. So we're part of this European project called Agile. So the goal of Agile is to enable more cyber-physical aircraft development. So the idea is to connect all these individual disciplines that are involved in aircraft design in a more efficient way. And one of the interesting sort of facts about Agile is that it's like a cross-continental collaboration between a lot of Concordia is the Canadian institution involved in this, but we're collaborating with a lot of institutions in Europe, and so each of these institutions brings a discipline to the project, and the idea is to sort of link all of them together to more efficiently design aircraft in a sort of a collaborative design environment. So part of that, and also relating to green aviation, is we're trying to investigate hybrid electric propulsion systems. So just to give you an overview, so hybrid electric propulsion system is sort of like a stepping stone to fully electric propulsion. So hybrid electric in the sense of your Priuses and your hybrid electric automobiles is what you would look for as a reference in the non-aerospace world. So in a conventional aircraft, you have your engine. So your engine provides thrust, which allows the aircraft to move forward and fly. But at the same time, your engine also provides non-propulsive power. So as Susan mentioned, you need some power to power your air conditioning, also to provide some heat to melt the ice on the wing, and you need electrical power as well. So traditionally, in just a normal aircraft, you have all these power flows that go from the engine to the various systems in there. So when we move to hybrid electric propulsion, you're using your fuel and you're also having an additional source of electric power from a battery. So you have two additional sources to provide both the thrust and the non-propulsive power. So when you go to hybrid electric propulsion, so these are some examples of aircraft or rather the Zunum aircraft which use hybrid electric power. So when you go to hybrid electric propulsion, you have the option of having different electric motors spread across different areas of the wing that provide the thrust. And in addition to that, you also have the battery which supplies electric power to different systems. So it provides both non-propulsive power to power the systems, and also power to provide the thrust to move the aircraft forward. So let's assume that this aircraft is hybrid electric. You see there's a whole bunch of propellers here. So each of these propellers could either be powered by fuel through a gas turbine engine, or fuel that charges a battery, which then powers the motor. And so you have all these different combinations and configurations that you could explore. And the challenges that come from this is that there's an increased complexity, and it's basically our entry into using hybrid electric power in aircraft. And so the first thing that comes to mind is that it's integrating both the propulsion system architecture. So essentially you can have different configurations of propulsion system and how that affects the aerodynamics in a synergistic way, and that brings in a challenge of complexity as well. And then there's system electrification. So can we use some of the power from the battery to power the electrical systems, and how much fuel does it save, and what are the benefits associated with that? And as I mentioned, here a large design space means like a large space of potential configurations and options for this hybrid electric architectures. And the challenge is to find the one that's, performs the best, but is also safe and is also certifiable, because there could be some options in there that are very good in terms of performance, but maybe not certifiable in terms of ensuring that the aircraft is safe to operate. Then, yeah, and so you have certification and safety challenges involved in that. And then also, in some cases, you might also have to see how the systems fit inside the aircraft. Can the battery be installed in certain areas of the aircraft? Because in conventional aircraft right now, you have fuel tanks in the wing, you have fuel tanks sometimes in the center fuselage as well. So how and where could these additional components be placed? And this is also something that we need to investigate when trying to see what hybrid electric configurations are useful. And the other thing that comes with more electrification in general, and the more use of more electric power and batteries and electrical components, is more heat is generated. And so having more of these components in general in the aircraft leads to more heat management problems. So you need to figure out how this heat can be removed. What is an efficient strategy to do that? Does that incur more weight penalty? So in order to remove the heat, you're adding more mass to the system. So then it sort of, does it balance out? And so that's another challenge with hybrid electric systems. And yeah, so this is what we're trying to do as part of the Agile project. And we're bringing in a lot of different disciplines and institutions in North America and Europe, and all of them are contributing a particular set of tools. And the goal is to sort of orchestrate the combination of all these tools to develop more efficient or develop all these hybrid electric architectures.
Okay, thank you very much. Questions?
Start with a question.
Yeah.
Are you looking at the combination of both solar cells with hybrid electric propulsion?
Yes, this is actually like a case study we want to do for like one of the next case studies, because it's very interesting. We have this problem with the hybrid electric that the batteries are actually heavier and take more volume than the fuel, so then you get into placement issues. But if you could get a portion of the energy from solar panels to recharge the batteries, so they could maybe be a little bit smaller. So that's actually a very interesting topic. So we're going to look into that. Yeah, but all the tools to do this kind of prediction need to be developed, which takes some time. But yeah, that's one of the case studies we're looking at. Yeah. Mm-hmm. No, we have not looked into that. So far, the assumption is that you would create like a smooth surface as you have. You need to have some kind of coating anyway to protect the solar cells. And so that's something we have just made as an assumption. But of course, looking forward, someone would need to look into what are these coatings, how is the surface different than like a normal aircraft surface, and then we would need to have help from people who can look into all these details of the aerodynamics. But yeah, that's something to be looked at. Another aspect with this respect is as well that, if you want to, the wings of the aircraft, for example, they are not fixed. They move and they bend, and so this is another aspect. How are the mechanical properties, and then how would that work with different layers of materials and so on. So that's another aspect. But there are already flexible solar cells that are developed. There are even solar paints that are investigated. However, they have very low efficiency. But at the same time, if they just replace the normal aircraft paint, then you don't have a weight impact necessarily and so on. So there's many interesting things that could be looked at in this respect. Yeah.
Solar panels, is there any of them is transparent?
Yeah, this as well. So there are some that are transparent. So that could be something, for example, for the cockpit windows as well.
I was thinking of the first.
Yeah.
If it's transparent, you can use for all the windows.
Yeah, this is actually something. Yeah, this is actually something I even looked at, I think, in 2014 with Bombardier. We had some, because there was some, I think, company, they certified their transparent material, and you were thinking, okay, if you put it on the windows of the aircraft, there's this effect if the sun is strong, so it shines on the windows, so you could automatically dim them, for example, by just using the power inside without using anything else. So that would be very interesting also for business jets and so on. But yeah, I mean, there's always the problem with new technology comes complexity, and then what we said, the risk to implement it, and you need the cost to certify it. So I think this is one of the things, also a question I wanted to ask is, how do we balance this cost versus the environmental benefit? So sometimes it just takes more money to develop these technologies. Where does it come from? Is there something that could be done maybe on a more political level that would help to develop these kind of new technologies? To, I don't know, from Icao side of view, is there anything you can comment on that?
So it's actually something that we actually take really, of course, you won't be surprised to hear, very seriously. So when we develop all our standards, we work on technical feasibility, so the manufacturing industry being able to actually deliver what the standard is telling them to deliver, or guiding them to deliver environmental benefit, interdependencies across noise, local air quality, and CO2, but of course cost. Because of course the cost is too big, then the standard is not. We always have to consider implementation in all of our work. So what we have is a committee on aviation and environmental protection, which is a group of states and observer organisations that develop the underpinnings of all our standards, and in that we do a very thorough cost effectiveness analysis of all our standards, and that actually you can see in all our work, which publicly available stuff, that we're not always able to pick the solution that gives the biggest environmental benefit. Sometimes we have to come down and give something that is economically reasonable. It's not to say you don't end up there eventually. Standards are made more stringent as the years go on, and technology evolves, and all this technology will fit into one of these standards one day, no doubt. But if I take our CO2 standard, we looked at a wide range of stringency options, but we weren't able to go all the way to the top, because all the way at the top would mean that we don't have any aircraft available to us to fly in. And actually, I don't think anyone wants that. No one's talking about that. We're talking about a balance of environmental benefit and economic reasonableness. We always have to strike that balance. So it's something that's really across all of our standards on environmental protection in Icao.
Is another question I had, is there any of them, for example, if they're in this offsetting scheme, is any of the money or the offsetting also directed towards the research on solutions that could bring more benefits in the future?
It's a good question. The answer is no, because the aspect of CORSIA that's very important to remember is that it's supposed to be a temporary measure. It's supposed to get us to carbon neutral growth, that aspirational goal set by the member states, while all the other things are coming on board. Now, I understand the question. Logically, you would imagine that you would take some money and then put it into the sector. But you also have to respect all the other sectors that are delivering the CO2 reductions that give CORSIA its power effectively. So we'll rely on an international marketplace of carbon emission unit credits and programs, and CO2 from aviation will be offset there, while we can't quite get there as a sector. When we can get there as a sector, actually CORSIA will end, So our ambition is clear, and I indicated at the beginning that the R in CORSIA means reduction in the sector, in fact, because it's trying to encourage sustainable aviation fuels. So the benefit is that your offsetting obligation under CORSIA, should you use a sustainable aviation fuel that's fully certified to be sustainable, then your offsetting obligation will reduce, and that will be the encouragement that part of the sector requires. The same is actually true for technology and operations. The more you reduce with technology, operations, and sustainable aviation fuels, the lower your offsetting obligation, so the less it costs. It's pretty straightforward economics, actually. And we'll see how that pans out leading up to 2035. The intention of it is to encourage all those measures to take over come 2035 and get us to carbon neutral growth, or indeed whatever the goal might be. You already mentioned the industry goal of 50% under 2005. That's an industry that's an industry goal. It's interesting to see how the industry sees how it can get there by then as well.
Thank you.
In regards to CORSIA, are you aware, has Icao done, or has anyone else done any sort of technology road mapping to look at sort of where we think we will be in the near term or long term based on current investments, current technology? Because from what I understand, we have significant underinvesting in sustainable fuels, if I understand correctly, the things that I've read. So yeah, just a question in terms of, and have we done those road mapping exercises, and then if so, where do we think we need more investment in terms of development?
So I mentioned our committee on aviation environmental protection. Actually, in the previous 3 years, our work comes in 3-year cycles. So in the last 2 years, we had an independent expert panel that looked at aircraft technology, so just on the technology piece, and looked at where it would likely be with varying different probabilities in 2027 and 2037 to tell us where we might go. That's very important for us because actually it forms the basis of our next standard setting process. So then we understand where the technology is going, and then the standards follow the technology in this way because they prevent the technology from being taken away from us. They prevent the industry from going backwards effectively. But actually, also on top of that, I mentioned in my slides we have a stock taking exercise. Actually, it's exactly to do this. It's to bring all the great and the good of the industry together to discuss exactly that point. The timeline is actually theoretically uncapped. Actually, I don't mind if someone comes to tell me that they're going to give me a technology in 2030, 40, 50, or onwards. What I want to hear is what the technology will be, what the CO2 reduction will be, how much it will cost, and what the probability is it comes to the market. Really, how the industry will deliver on its commitments, whether it's an industry commitment of 50% under 2005, or whether it's carbon neutral growth in 2020. How are we going to do that? And then what I'll finally say is that we will hear in the next couple of years of a long-term goal for aviation agreed by Icao member states. There's plenty of work to do there, but what we're told is to prioritize that. And so our member states really take that very seriously. So we'll see where that goes. And of course, it responds to international aviation doesn't sit formally mentioned. It's not formally mentioned in the Paris Agreement, but of course, it responds to those same concerns. That's why we have CORSIA. That's why we have our basket of measures, and that's why we'll have all this work on a long-term goal. So actually, it's an exciting future, I think, for aviation, and an exciting technology roadmap that we'll see. And we see a number of states now coming out with varying different technology roadmaps, whether it's the industry driving it or the state itself. I happened to see in December, the UK, country that I'm familiar with from a previous existence, has an industry roadmap towards net zero. That's an amazing commitment, and it's interesting to see how we'll deliver it with all the challenges we hear about electrification and solar panels and aircraft and so on.
Yeah. Go ahead.
So I guess related to that for Icao, so the net neutral growth is sort of like at the bare minimum, we should at least stop opening the tap, right? Do you have a sense for, you know, how long it will take to get to the point of saying, okay, let's start closing it, and bringing the aviation emissions down to zero? Do you have a sense of kind of what the timeline is for that?
Yeah, that's a tricky question. So what I know is we have CORSIA till 2035. So I know that, or beyond. I suppose it depends how successful we are. And I know that the current ambition, this aspirational goal, is carbon neutral growth at 2020. What I also know is that we've been told by our executive body, our 193 member states, to prioritize the work on a long-term goal. Now, I don't know what that means, and I don't quite know the timeline, but what I do know is they told us to prioritize it and deliver something on it by the next Icao assembly. So that's in 3 years' time. So that means we're told to work on it. That's a clear mandate. And really, in the next, even in the next few weeks, we'll know more about that process moving forward. But really, underpinning all that is Icao member states can set these goals, but of course, really, the industry is the one that will have to deliver these CO2 emissions reductions. So it's really important to see all these roadmaps moving forward. I think technology, maybe Alejandro can help me. Technology roadmap from IATA, I think a few weeks ago, that painted a picture of blended wing bodies in the future and so on. This is really important to see. And so we know that we have to investigate this from the bottom up. So we have to understand what the industry can deliver, what we can do as a sector. So that's what we mean by prioritizing the work on a long-term goal. The other one from the top down, that's a different argument. How much we should deliver, that's a very, very challenging intellectual exercise to imagine how much aviation should actually deliver, how much it should be responsible for. So we'll take it from the bottom up and investigate how much the sector can reduce itself.
I think just to add on what Nick said, you can hear me. We have seen a number of states like the UK or the Netherlands and Germany as well, and companies that are committing to goals beyond that, so beyond the carbon neutral, so net zero and all that. So just a compliment on your question, right? Although we haven't seen this on a global scale yet, but we do see these initiatives popping in different parts of the world where people are trying to elevate their ambition into different objectives. Net zero, minus 50%, carbon neutrality, etc.
Do the UK, German, and Dutch goals include international flights, or do they just include domestic flights in their goals?
It's interesting because the UK industry goal appears to include international flights because it talks about
Trump's CORSIA then?
No, actually it doesn't. It talks about in-sector reductions. It doesn't and it actually talks about CORSIA and the importance of CORSIA, but it's actually an industry goal from the UK. So we have to be careful when we talk about those kind of goals, because I don't believe it's a UK government goal. Although of course the UK has actually committed to I think the first country to commit legally to net zero as a nation. So, but it is with our stock taking seminar that will come up in 2 months. What we've tried to do is engage the players that have those roadmaps. So, for example, you can see that some of the engine manufacturers have these clear roadmaps where some of them are even talking about skipping a generation of technology, which seems like an amazing leap for a manufacturer to skip a generation of technology. But skipping a generation of technology, I think, or Rolls-Royce, for example, with a 2030 net zero aircraft, regional jet. These are the kind of people that we'd like to come to our seminar to tell us how they're going to deliver on how far they can go in terms of climate change commitment.
Well, a lot of these goals are also a holistic approach, right? So none of them, I can tell you that none of them only rely on technologies or only rely on fuels or only rely on market-based measures like CORSIA. They use kind of everything. CORSIA, other market-based measures that they could potentially imagine, technologies, aviation fuels, operations. So these are scenarios that bring together the whole lot.
And that is a very, very important point, because in all our work, we talk about this basket of technology, operations, and fuels, and we talk about CORSIA as the complementary measure.
So prior to the carbon neutral goal for 2020, there was a commitment from the industry to reduce from 2009 to 19 to reduce by 1.5% every year. So are there any numbers on whether they achieved that?
I haven't seen any numbers from the industry. I mean, it's certainly a big challenge to reduce year on year 1.5% or 2% as the Icao aspirational goal. But I haven't seen any industry numbers. I don't know, Alejandro, whether.
I think, well, from what I know, I think so far they've achieved it, but they predict that it's gonna slow down.
That's what I think that I've seen, that it's been 1.5, and I think, like you said, the aspirational goal is 2%. So what I've been reading is that sort of a lot is required to go from this historic 1.5 to 2. Right?
Yeah, because these percentages, it's not like, from here to the next year we reduce 1.5, but it's actually you take a period of time and then you introduce an aircraft which is 20% more efficient, and then you buy that efficiency, and plus so you buy the whole lot over a period of time. And the thing that we're seeing now is a big replacement of aircraft currently being undertaken right now. So A320neos, 737 Maxes, A350s, 787s, all of these new generation aircraft are coming into service, which are going to bring the emissions down considerably. But then these aircraft stay airborne for 20 years. So, and this is one of the big challenges that we've seen, is that a lot of these approaches depend on the fleet rollover, which is very slow. And this is why CORSIA was important, because we know that, and we know that even if we came with a technology today, it takes time for this technology to penetrate the market. Then with complementary measures to be able to do it. Whereas, for example, drop-in aviation fuels, they don't depend on the fleet rollover. That's something that you can deploy and put on the aircraft, and you don't need for an aircraft to be developed and certified, which is 10 years. You take 10 years and then credit the market.
To follow up on your question and also other discussions, is there any Icao can play a role in for research funding things in terms of strategize the project? We have, I don't know how familiar you are with our funding systems in Canada. We have a new funding formula, we call it Alliance. It's very interesting the way that they put it. It's very recent. It goes all the way from almost no commitment from industry and all the way to very much in-kind and cash contribution. But I was thinking during this discussion, if you can prioritize or we can strategize this effect, like if Icao, for example, prove this thing, the project will be very much in that direction, so it doesn't necessarily need a lot of cash or in-kind from industries, but we know this is important for, let's say 2035, this is what we are looking for, and this project falls into that category. Does it make sense? I mean, can Icao play a role in that to bring this together?
So you won't be surprised to hear we don't fund projects ourselves. Although I'm heard there's a really nice ambula behind here that we've in terms of concepts, but we don't fund projects ourselves. Where we can help and where we have a long history of helping as a UN specialized agency for international aviation is bringing people together. So bringing researchers together, such as yourselves, with all the stakeholders. So I don't want to sound a bit like a broken record, but actually coming to this stock taking event is a joining the dot exercise, right? Joining the member states with industry, with all the research community stakeholders that maybe do communicate, but maybe don't communicate on those kind of levels. So then people can see what the real ambitions are and what the real technologies might deliver in the future is a really important role Icao can play as that forum of bringing people together. Now, I talked obviously a lot about us developing standards and recommended practices. That's our reason to be, of course, but bringing everybody together is also part of it. So that's how we can really help. I could not say as a UN official that, you know, one technology is better than others. But what we do is, with in-kind resources from our member states, run, say, independent expert reviews, try and look across the piece at absolutely everything, and then run numerous events to try and bring people together in this kind of open forum.
Thank you. It's 6 o'clock, but if we have other burning questions from the audience, we can maybe take a last one. No? Okay. So now I thank everyone for their contributions, for the discussion, the audience for listening and asking questions, and I hope we'll maybe have some more collaboration in the future on some topics. Okay.
Thank you.
Thank you.
Oh, good. Okay, so you're safe.